Welcome to the debate. Today, we're diving deep into, well, one of astrophysics' most compelling and, frankly, enduring mysteries, dark matter. Now, the concept of unseen matter might sound a bit like science fiction, I suppose, but a rapidly growing body of evidence, including some very recent observations of galaxies with truly unusual matter distributions, has really propelled this hypothesis right to the forefront of cosmic understanding.
Absolutely. It's a fascinating puzzle.
It is. And the central question we're exploring today is this. Do the observations of galaxies seemingly devoid of dark matter, or where dark and ordinary matter have clearly been separated, do those observations, combined with some pretty compelling theoretical arguments for new particles, truly solidify the case for the existence of specific dark matter particles as the main explanation for how our universe is structured and, well, how it moves? Now, I'll be arguing that this diverse evidence provides direct and compelling proof for dark matter's existence and, crucially, for its specific nature as a particle. My esteemed colleague here, however, will contend that while these observations undeniably necessitate new physics, I think we agree on that, interpreting this solely as dark matter particles is perhaps just one solution within a much broader, more fundamental need for new elementary particles and forces rather than, the only possible conclusion.
That frames it well.
Good. So let me start. I find the convergence of evidence for dark matter truly overwhelming, actually. It's quite remarkable how multiple, entirely independent observational windows, from the smallest galactic scales right up to the largest cosmic structures, they all consistently point to the same conclusion. There's just something massive out there we can't see. We've known for decades about the anomalous rotational velocities of stars and galaxies, right? First noted by Jan Oort way back in our own Milky Way, then spectacularly confirmed by Vera Rubin and W.K. Ford in Andromeda, and, well, dozens of other spiral galaxies. Their work showed stars orbiting so fast at the galactic edges that the visible matter alone simply couldn't hold them in. It just doesn't add up. Beyond that, we see strong gravitational lensing. For instance, in massive galaxy clusters like Able 2218. Light from distant galaxies is bent and distorted by far more mass than we can visually account for. It's like seeing through a warped lens caused by invisible weight. And perhaps most precisely, the cosmic microwave background, CMB measurements, offer really our most precise window into the early universe. The specific pattern of peaks and troughs we observe in the CMB's temperature fluctuations, it's exquisitely sensitive to the universe's composition. And here's the thing. Computer simulations without dark matter completely fail to reproduce these patterns. They just don't work. Whereas models that include a specific proportion of cold, non-baryonic dark matter fit the observations with remarkable accuracy. So this isn't just about missing mass. It's confirming a component that behaves distinctly from ordinary matter right from the universe's infancy. And of course, the observed large-scale structure of the universe itself, this vast cosmic web of galaxies and voids, it simply cannot form the way it has without this gravitational scaffolding provided by dark matter. But let's turn to some more recent and, I think, incredibly direct support. Take galaxies like DF2. These appear to be almost entirely devoid of dark matter. And what do we see? These galaxies are observed to be losing mass, becoming diffuse, their stars moving at remarkably slow speeds. Now, this behavior is precisely what we would expect if they've been tidally stripped of their dark matter by interactions with other galaxies. This directly demonstrates that dark matter is absolutely required to hold ordinary matter together in gravitationally bound structures. Without it, these galaxies would simply, disintegrate over time. This isn't just inferring dark matter's presence, it's seeing the consequences of its absence. The very fact that the lack of dark matter causes these galaxies to be unstable, paradoxically offers compelling proof of its ubiquitous and essential role. Furthermore, the bullet cluster, this is a critical, almost irrefutable example. Here, gravitational lensing clearly shows a dramatic separation of dark matter from ordinary hot gas during a high-speed galaxy cluster collision. The hot gas, the ordinary matter, it interacts electromagnetically, right? So it got slowed down by drag, creating these pink clumps in the images. But the dark matter shown in blue from the lensing map, interacting only very weakly with itself or the gas except through gravity, seems to have passed straight through. This kind of separation simply cannot be explained by alternative theories of gravity that don't posit new particles or forces. It strongly indicates that dark matter is indeed a form of matter that interacts predominantly through gravity, precisely what we expect from a dark matter particle. And finally, the missing satellites problem. This was a big headache for a while, but it's largely been resolved by realizing that many dwarf galaxies are actually what we now call dark galaxies, essentially subhalos of dark matter without visible stars or gas. This was exactly as predicted by the lambda cold dark matter lambda CDM model, our standard model of cosmology, and it's subsequently been confirmed by gravitational lensing observations in clusters like Coma and Virgo, where hundreds of these dark structures have now been found by teams like Kadagias and Mijas. So, this confluence of diverse observational lines, all cross-correlating to consistent results across vastly different scales, coupled with this clear theoretical necessity, strongly supports the dark matter particle hypothesis as the most robust and predictive explanation we have.
Okay, they appreciate that thorough presentation of the observational evidence, and I agree wholeheartedly that a significant amount of invisible mass is unequivocally at play in the universe. I mean, observations like galactic rotation curves, gravitational lensing, the CMB, they undoubtedly point to the limitations of our current understanding, either of gravity or, the composition of the universe. No question there. However, I believe the leap to conclude that this solely constitutes specific dark matter particles needs, well, a bit more nuance. My perspective is that the need for new particles is in fact a really fundamental requirement across various theoretical frameworks, quite independently of these specific astrophysical observations you've cited. We're talking about profound internal consistency issues within physics itself. I mean, think about it. From early concepts like Einstein de Sitter's model predicting unseen matter, way back, to modern theories attempting to stabilize the Higgs boson mass, and even grander frameworks like superstring theory and supersymmetry, new particles beyond our familiar standard model are explicitly required to, complete symmetries or resolve deep theoretical inconsistencies. These theoretical necessities underscore a broader shift in our understanding of fundamental physics, hinting at a universe much richer in elementary constituents than we currently observe directly. That's a compelling argument about the bullet cluster in DF2. And I absolutely agree that phenomena like these showcase interactions that directly challenge simpler alternative gravity theories, those that don't posit new particles. They certainly push us towards something new.
But the key takeaway for me from the theoretical arguments, and as the source material itself points out, is that, quote, new particles, which means new types of matter, is required to explain observations and complete symmetries, end quote. This crucial point leaves open the specific nature or identity of these particles, doesn't it? The issue isn't whether there's something new, but what precisely that something is, and whether dark matter particles as a singular, specific, weakly interacting entity fully encapsulates the breadth of possibilities. I mean, even modified Newtonian dynamics, MOND theory, which proposes altering gravity's laws at very low accelerations, in its more developed forms, its relativistic versions, it often requires additional particles, like sterile neutrinos, to fully account for observations, particularly gravitational lensing in galaxy clusters. And the amount of mass needed for these particles, it's staggering, equivalent to slightly more than the entire ordinary matter content of the observable universe, potentially 2 trillion galaxies worth of baryons. This just illustrates that the need for new unseen matter is a pervasive theme. It's not just exclusive to the standard dark matter particle paradigm. Furthermore, while the lambda cold dark matter model is undeniably successful at large scales, as you said, it still faces challenges at smaller galactic scales. The core and cusp problem, for example, highlights a persistent discrepancy. Simulations within the lambda CDM framework consistently predict a sharp, dense spike of dark matter at the center of galaxies, what we call the cusp. But observations again and again show a much shallower, less dense distribution, the core. This suggests our current understanding of dark matter's microinteractions might still be incomplete, even within the particle paradigm. Perhaps
weak self-interactions among dark matter particles themselves, or subtle cross-interactions with ordinary matter are needed. So the argument isn't against the existence of additional matter or new physics, but rather whether labeling it definitively as dark matter particles fully captures the breadth of possibilities suggested by these deep theoretical necessities. We are talking about a fundamental requirement for entirely new elementary particles across the board. And while dark matter is a prime candidate to fulfill some of this requirement, it's potentially just one solution among possibly many new types of matter and forces, some perhaps existing in entirely separate dark sectors. The more fundamental question really is, do we need new particles and forces? And every major theoretical framework, from supersymmetry to string theory, resoundingly says yes.
I appreciate you framing that broader theoretical landscape, and I absolutely agree the necessity for new physics is profound. However, what truly compels me towards specific dark matter particles is how the bullet cluster provides such unequivocal, almost visual evidence of a distinct substance behaving in a very specific way. It's not just about new particles in some abstract theoretical sense, it's about matter behaving identifiably. The ordinary matter, the hot gas, it interacted, it slowed down. The dark matter component just passed through, almost as if it didn't feel the collision at all, apart from gravitationally. That implies a particle that interacts extremely weakly with itself and with ordinary matter, exactly as the standard dark matter particle hypothesis posits. How else do you explain that clean separation? It's hard to see how a modified gravity law alone could achieve that. And building on that idea of dark matter's distinct behavior, let's circle back to DF2. You've emphasized the role of new physics generally, but doesn't DF2's observed instability provide a remarkably clear demonstration of what happens when that specific, weakly interacting dark matter component is absent? We see stars moving at a fraction of the speed expected if it contained the usual amount of dark matter, and the galaxy is, well, effectively disintegrating. This observation directly links the presence of dark matter to gravitational binding. It shows what happens without it, and this consequence is perfectly aligned with the dark matter particle explanation for cosmic structure. It's hard for me to imagine an alternative, new particle explanation that so neatly accounts for both the bullet cluster separation and DF2's instability.
I'm sorry, but I just don't think this completely closes the door on broader interpretations. Let me explain. While I concede the bullet cluster's significance, especially in ruling out simple modified gravity theories that don't posit new particles, I'm curious, doesn't the source material itself acknowledge that even advanced modified gravity hypotheses now often require new particles and forces? You mentioned MOND needing potentially more mass in sterile neutrinos than all the baryons in the universe.
Well, yes, some relativistic versions do incorporate fields or particles.
Exactly. So if that's the case, how does the bullet cluster's evidence uniquely constrain us to specific dark matter particles rather than simply confirming the broader need for entirely new fundamental constituents, whatever they might be? The point about MOND meeting a substantial amount of new unseen particles, even while modifying gravity, actually reinforces my argument. The universe seems to demand additional non-baryonic components, regardless of the precise theoretical framework. The dark matter we observe gravitationally could be an emergent property of a more complex hidden sector of particles and forces rather than just a single, simple, weakly interacting massive particle, or WIMP. The critical point is that these new fundamental constituents might be vastly more complex than a single, simple dark matter candidate. The sheer theoretical necessity for new particles arises from these deeply rooted issues in physics, things like restoring broken symmetries, stabilizing the Higgs mass, completing grand unified theories. These aren't merely astrophysical fixes cooked up to make observations fit. They are fundamental theoretical gaps demanding answers. So while the bullet cluster clearly shows something non-baryonic acting gravitationally, it doesn't definitively constrain the type of new matter, nor does it preclude an entire dark sector with its own complex set of particles and forces that interact only weakly with our own, potentially giving rise to the phenomena we currently attribute, perhaps simplistically, to a single dark matter particle.
That's an interesting point about the complexity, though. I might frame it slightly differently. The resolution of the missing satellites problem through discovering numerous dark galaxies via gravitational lensing is incredibly powerful precisely because it showcases the predictive power of the lambda CDM model, which is fundamentally built on the dark matter particle hypothesis. For years, the lambda CDM model predicted hundreds, maybe thousands of dark matter subhalos around larger galaxies, yet we only saw, a few dozen visible dwarf galaxies? This discrepancy was a major puzzle, the missing satellites problem.
Right, a well-known tension.
Exactly. But as our gravitational lensing techniques have improved, we've started finding literally hundreds, maybe thousands of these dark, starless galaxies in clusters like Coma and Virgo. This is a clear case of dark matter not just being a theoretical fix, but having concrete, observable, if indirect, manifestations that validate the predictive power of the lambda CDM model specifically. It's a prediction made based on dark matter particles that has been borne out by observation. And this isn't just about the model's flexibility to accommodate new physics, it's about a consistent predictive framework. The consistency across vastly different observational methods, lensing, rotation curves, the CMB, large-scale structure formation, all pointing to the same amount of missing matter, roughly 5 times the amount of ordinary matter, lends profound credibility to the dark matter hypothesis as a unified, coherent explanation. It's not just new particles in general, it's new particles with very specific properties, cold, non-baryonic, weakly interacting, that are consistent across vastly different scales and cosmic epochs. That consistency is a powerful argument for their specific nature.
I'm still not entirely convinced that resolving the missing satellites problem, or frankly, the adjustments needed for the core and cusp problem, like assuming weak self-interactions or other subtle behaviors, truly confirms a specific singular type of dark matter particle. To me, it demonstrates the considerable flexibility, maybe even the tunability of the lambda CDM model to incorporate new physics when confronted with inconvenient data. The very fact that the model needs these adjustments to better fit observations like the core versus cusp issue, perhaps implying dark matter self-interactions, suggests a more complex interplay. It could hint at new particles and forces, maybe even an entire dark sector with its own set of rules and interactions, rather than a single, simple, non-interacting dark matter candidate. This points, I think, to a deeper, more intricate reality than a singular dark matter particle explanation might imply, echoing that fundamental theoretical call for new constituents we discussed. And while I absolutely concede the remarkable consistency of the observations you've highlighted, the convergence is impressive, no doubt. I must pivot back to the theoretical necessity aspect. The fundamental drive from Einstein de Sitter's early work to modern supersymmetry and superstring theory is to explain observed symmetries and close these fundamental gaps in the standard model of particle physics. The most important takeaway here, as the source material itself notes, is that new particles, which means new types of matter, is required to explain observations and complete symmetries. That feels like the bedrock issue. The possibility that the universe contains many new particle types, perhaps interacting within dark sectors that couple only very weakly to our ordinary matter, is arguably a more profound implication than simply identifying dark matter as a single uniform substance. It's really about recognizing the fundamental incompleteness of our current picture of elementary particles and forces. The dark matter particle is a compelling candidate, yes, but perhaps not the only answer to that deep, pervasive theoretical need.
Okay, to summarize my position then, the convergence of multiple, diverse lines of observational evidence. I'm thinking particularly of the direct and indirect detection of dark matter's gravitational effects, its unmistakable separation from ordinary matter in the bullet cluster, and its essential role in maintaining galactic stability, which is so strikingly evidenced by galaxies like DF2 and also by the resolution of the missing satellites problem. All this provides truly robust support for the dark matter particle hypothesis. These phenomena demand a physical explanation, and specific dark matter particles uniquely fulfill that need, offering a comprehensive and remarkably consistent solution to the universe's observed structure and dynamics across all scales. The fact that all these different methods consistently point to the same amount and the same specific behavior of this unseen matter strongly validates its existence as a distinct, weakly interacting form of matter.
And I'll conclude by, again, acknowledging the absolutely compelling nature of the observational evidence for unseen mass and the undeniable necessity for new physics. I think we're in complete agreement there. However, I want to reemphasize that the fundamental requirement, as pointed out by numerous theoretical models across different branches of physics, is for additional elementary particles and forces beyond our current standard model. While dark matter, as you've described it, is certainly presented as a very strong candidate to fulfill some of these requirements, the broader implications suggest that a deeper understanding of new matter and fundamental interactions is still unfolding. This debate, I think, really illuminates the profound questions that remain about the fundamental constituents and forces that actually shape our universe. It's about recognizing this pervasive need for a richer particle landscape than we currently know.
Indeed. And I think we both agree on the significant progress that's been made in understanding the universe's composition and also on the exciting prospect of further discoveries regarding, well, new forms of matter and fundamental interactions. There is certainly more to explore in the material, and our journey to fully comprehend the cosmos is clearly far from over.